In this video, we will talk about the step 10, fine-tune the PID controller. From the previous video, we used the Ziegler-Nicholas method and TI Portal fine-tuning method. Basically, we get one group PID parameters. And after the step 8 and the step 9, we can base on those PID parameters and based on the actual process performance, we can fine-tune our PID controller. And also in this video, I will show for the gain, integral, and the derivative value, what the role of those PID parameters. For example, to increase and decrease the gain, integral, and the derivative, what the behavior will be, what the process value will be changed. Okay, let's go to the TI Portal side. And currently, our PID is running in its auto mode. Currently, the set point that is 50. PID parameters, they come from the automatic fine-tuning. That come from the previous video. So currently the gain that is 70, and the integral that is 14.9, and the derivative that is 3.74. And in this video, I will individually change the gain, increase and decrease, and let's watch the behavior of the PID control and the feedback. Firstly, let's set this set point with this parameter. And firstly, let's use this parameter as a reference and set the set point from 50 to 45 and from 45 to 50. And currently this process is working in a stable status. And now let's change this setting point from 45 to 50. Okay, so this is a transition time that takes 1 minute for this decreasing, with this gain 70. With the current reference PID parameters and with this dropping and rising this transition time, we will use this curve as a reference compared with other PID parameters changes. Let's increase this proportion gain from 70 to 120. Let's increase a lot. We will see the difference. And after this change, let's wait for a while, waiting for the system go back to its stable status. And keep in mind, currently I didn't change the set point. As we can see, even if I didn't change the set point, the control signal already changed a lot. That's because this gain is very sensitive according to that feedback noise inside the process feedback. So the system become very sensitive and not quite stable. Which means sometimes if we increase the gain, even if this higher gain can make your system respond very fast or quicker than before. However, this output, this oscillation on the output will cause your actuator worn out or fail quicker than normal. That means this gain 120, this parameter is so high for this system. So for testing well, we could decrease this gain from 120 to 100 to test a higher gain on this system. 120 is still a big value for this system. I didn't change the set point. And as we can see, after we change to 100, decrease the gain, so this output can ramping down. Alright, so from here, let's decrease this set point. As we can see, with this a big value on the gain, so the output is very sensitive, and this amplitude changing on the output the amplitude is really huge. So that makes the system is very sensitive on the process change. Since a higher gain on the PID, this PID control will be very sensitive about this process value noise and the process change. So if your process value has a noise and your actuator has a mechanical elements, you better not set a higher gain because your actuator will run out very soon. With this change, we can see that. So the actuator will open close frequently. Okay, so now this is a set point change from 45 to 50 with still a higher gain, that is 100. We can see during this transition, the output is still very sensitive. Alright, that is the higher gain. So next step, let's test a lower gain value. So let's change this gain value from 70 to a very low value. For example, let's set 5 or 10. A very small value on the gain. Alright, now the system is going back to its stable status. And let's change this setting point from 50 to 45. So as we can see from this falling process, because our proportion gain that is a very small value, so when the system reach to this setting point, the PID cannot give a fully power on this output. So it still changes slightly. So that's why this process value go across this setting point and have an overshoot. With this smaller value, the output of the PID cannot give a higher value on the control. So that's why this process value has an overshoot here. Okay, let's set this setting point from 45 to 50. So as we can see, when the process goes across this set point, this output cannot react in time and cannot give a higher value on the control because this gain is really small. So its response is still smooth. So it cannot have a strong power on the control. That's why it gets a overshoot. The overshoot is very common in practice. So when you try to decrease the overshoot, maybe one way you can increase the gain of your process system. But keep in mind, your increase cannot too high. Otherwise, it will shift to the first scenario when the gain is too high, the process is really sensitive. So that means the gain must be a certain range, cannot too high and cannot too low. Because too low, it will cause this overshoot, but too high, it will be very sensitive about the noise. In practice, sometimes a lower gain also will cause the system unstable because your control system is not powerful enough. So with a lower gain, sometimes the PID cannot totally hold the system. So your process system still could be very unstable with a lower gain. So that means our gain need to be a certain value, cannot too high and cannot too low. Okay, so let's retain this gain to 70. And let's wait for a while and wait for this process going back to its stable status. Now let's give a new set point change. This is our reference PID parameters. Alright, in next step, we will test. I will decrease or increase the TI, change the integral value on this PID controller. And let's see what the behavior of this PID controller and what the behavior response of this process value. before I change the integral value of this ti parameters, we will return the k, ti, and td parameters. And also I will change the side point and use this curve as a reference curve. Okay, this is our reference curve. This curve comes from this reference PID parameters. And from here, I will increase this integral value. And once this value got increased, that means our integral infacts that will be decreased. So let's change to 80. And after this system becomes stable, let's change the side point from 50 to 45. So from here, let's compare. This is the TI value of 14.9 we used before. This is the new TI value we increased to 80. So we will see the system take a longer time to reach the set point because that integral got decreased. The system need a longer time to eliminate that error between the process value and the set point. As we can see, since this integral in fact got decreased, so the error between the set point and the feedback, that error is eliminated slower than before. So after this integral value got increased, this result shows a so huge difference. We will only test this one time. After this, let's decrease this integral time. Change from 80 to 3. So the original value, that is 14.9. Decreasing this TI parameter, we will enhance the integral infacts. And also we can see after I change to 3, so this error between the set point and this feedback eliminated very soon, because currently this integral already enhanced by this decreased value on the TI. From here, let's set from 45 to 50. And this curve, this rising curve, that is our original reference curve. And let's see this time. With this enhanced integral infacts, so the process value got overshoot. Apparently, this is a big overshoot here. That's because the behavior of our PID controller, that is really slow. That's because this integral infacts is too strong. Okay, so from this 3, let's change to 10. And let's see next time. And I will change to 45. Okay, let's change from the 45 to 50 again. So this curve comes from the integral value that was 3. And now I change the integral value to 10. Increase this integral value to decrease this integral infacts. This overshoot should be decreased. Yes, it is. So after we increase this integral value to decrease this integral infacts, so this overshoot got decreased. Okay, so that is the integral value. We increased and decreased this value. We will see there are so huge difference. Alright, that is the integral test. In next step, we will test the derivative. To test the derivative, firstly, I would like to prepare the system and let the system has a little bit of overshoot. And to create a little bit of overshoot on the system, firstly, I can decrease this TI to enhance this integral infacts a little bit. I will decrease the TI to 5. Again, this is used to prepare the system has a little bit overshoot. So I decrease the TI to 5 value. And we can see with this set point change from 45 to 50 and from 50 to 45, this 2 times, we can see the system has a little bit overshoot. This used to prepare the next test. And from here, let's firstly increase this derivative action. That will increase and improve this derivative in fact. Okay, so now I will change to 8. Okay, let's change from the 45 to 50. As we can see, in this case, after we increase this TD, this derivative, the control output become very sensitive, and this control performance actually become worse than before because it gets a higher overshoot. The output has a huge oscillation here. And let's set a new set point with this higher derivative value. Okay, from this following process, we will see this output control from the PID is very sensitive. Here it comes up one topic. In some plant, after this process start run 1 or 2 years, the maintenance team will find the actuator and the valve controlled in this PID loop. They will run out and defective very soon. The one of the reasons may be caused by this. You will see, even if this process can be controlled, but from the output control curve, this right curve, you will see it oscillates with a huge amplitude. So for the mechanical devices and some valve actuators, they will run out very soon with this control. So under this condition, sometimes we need to check out the gain and the TD parameters for your PID loop. A huge parameters on the gain and derivative will cause this oscillation on the output. We need to prevent this happens. Okay, so this time let's decrease this value, change to 0.5. And then let's give a new set point. Let's compare. So this is a very interesting behavior. We will see the process value according to this control signal oscillation. The process value by this output oscillation, it will oscillate like this. The reason why it shows this, that's because we set 5 value on the integral value. That makes the system has a very strong integral effects. With a value on the derivative that can counteract on this integral effects. However, once we decrease this derivative value, that actually makes this integral become stronger than before. So that's why the system shows like this. Meantime, comparing with the previous curve, we can see after we decrease the derivative value, the output no longer show that higher oscillation there. But to solve this current, this green curve, this behavior, we can increase the integral value to reduce the integral effects for this PID controller. So we can try to increase this TI value to reduce the integral effects. Let's try to change from 5 to 10, or even we can try 14. And then we will see after we increase this TI parameter, the oscillation of this process will decrease and return to this stable status. Okay, let's give a new set point. From this green curve, we can see that is the process feedback. And it looks like the system is approaching the set point, and it shows a very hesitate. That's because we decrease the derivative. The derivative is kind of like a prediction function of the PID. So after we decrease this derivative parameter, the system, the PID controller, loses its prediction function. So it shows a hesitate to approaching that set point. Okay, so let's change it again from 45 to 50. The current TI, this is a 14. Comparing this TI was a 5. The process behavior shows better than before. Okay, with the current integral value, let's increase this derivative and compare this area. Okay, let's change from 0.5 to 3.5. And let's set a new set point, 45. And compare here. As we can see, with this enhanced prediction on the derivative, so the process value will not show that hesitate behavior. See, like this. And then let's change this 45 to 50 set point. As we can see, after we increase the derivative, the previous that hesitate behavior is gone. So now the process shows very perfect. Alright, that is for today. In this video, we change this gain, integral, and the derivative individually to check out the behavior of the PID control and the process value behavior. And during the test, the system sometimes shows oscillation, sometimes it shows overshoot. Those behavior are typical response. Hopefully, those tuning direction could give you some idea when you do the fine tuning. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.